Okay, so here we have our next question on the menu today, and it is asking us this situation. So find the force, the magnitude of the force on charge Q, where Q is 3 microcoulombs, and given this diagram. Okay, so we have to find the electric force. Okay, so we know to calculate the electric force. We have F electric is equal to K Q Q, or not, let's not use the same Q. K small q capital Q, because this is going to be the force between two charges. And you know, that's why we want to have different Q values. So we have a lowercase q and an uppercase Q, and this is all divided by R squared. So this is where K is Coulomb's constant, 9 times 10 to the 9, nice and easy to remember, multiplied by, and the Q values are charges, and the R is distance between charges. Okay, so in this situation we have this is what's going on. So we have let's draw this out. This is our Q of interest. 3 centimeters downwards from here, we have a charge here. Let's call this, or we say negative Q. Okay, and directly horizontal from there, we got 4 centimeters. Let's write this out like in base SI to make this easier to calculate. Here we have our other charge, which is 2Q. Okay, so essentially what we want to do here is we want to find the force as felt by Q. So FQ, oops, is going to be equal to the contribution of F negative Q plus the contribution from the force of F2Q. Okay, so given this, we know that our original formula for the electric force is like this, but whoa, we got to keep in mind that this is going to be a vector value. So we do need to have a direction associated with this. So as we can see here, another thing that we should add to our diagram here is you see that the distance between, you know, the Q of interest and the 2Q, that's not given to us directly. We need to solve for that. So let's call this R3. This is going to be the hypotenuse of 0.03 squared plus 0.04 squared, which is 0.05. Yeah, 3-4-5 triangle. It's you'll see it fairly commonly. Okay, so this is going to be the R value associated with 2Q, and the R value associated with negative Q is going to be R1 here. Okay, cool. So given this, we can we need to give some directions to our stuff, and when we have our magnitude of F negative Q, so without the arrow on top, that just means the magnitude that we're interested in. Without this, we know that our direction, let's have our y be this way and our x be this way. X is associated with the unit vector I hat, y with j hat. So with the direction of negative Q, it's just going to be in the j direction. Okay, now when we have our F, we need to calculate our force magnitude as a result from the 2Q. This is going to be a little bit more complicated. So we're going to have a negative I component. Negative I because, we're put, like, these are going to have the same sign of the charge, Q and 2Q. They have the same sign, meaning that they're going to be repulsive. They're going to try to get farther away from each other. So if Q is going to try to get farther away from 2Q, it's going to be in the negative X direction. Okay, so it's going to be negative, and it's going to be 0.04 over 0.05 in the I direction. The reason why is because you want to take the direction of interest divided by the hypotenuse, and that's going to be the factor associated with that. Okay, and in the J direction, it's going to be positive. And because it's positive, it's going to push it upwards. So because they're repulsing, and for this, it's going to be 0.03 over 0.05 in the J direction. Okay, so given that we have these unit direction vectors, we just need to sub in our values for these, and then we can have our proper vector value. Okay, so FQ is equal to FQ negative Q, so that's going to be KQ times negative Q. So because we have the negative Q here and they're going to be attracted to each other, it's going to be in the negative J direction for this. And since the negative comes from here, we don't want to put it there. So keep these things in mind. So it's going to go downwards, and the distance for that is going to be R1. R1 in the J direction. Okay, now we have plus K for the Q2. So we have KQ 2Q over R3, which is 0.05 meters, multiplied by negative 0.8 I plus 0.6 J. Okay, so that was just converting these coefficients here into 4 over 5, 3 over 5, 0.8, 0.6. Makes sense. Okay, so let's expand out our term over here. So we're going to have FQ. And we can also collect our like terms, but we'll do that in the next step. Q squared negative R1 in the J direction plus K plus 2K Q squared over R3 in this direction, 0.8 I plus 0.6 J. Yep, and let's expand this out a little farther. Negative K Q squared over R1 J minus 0.8 times 2 KQ squared over R3 the I direction plus 0.6 times 2 KQ squared over R3 in the J direction. Okay, so let's collect our like terms. So all the I terms will go together, all the J terms will come together. And we can factor out the things that are common to it. So the only I term here is negative 1.6. So that's combining the times 2 and the 0.8 times KQ squared over R3 squared. Oops, that's a big goof of me. You want to make sure that all of these have the squared on the denominator. That can definitely get you hurt pretty bad if you make the mistake and don't catch it. Okay, let's collect our j terms. So we're going to have plus 1.2 kq squared over r3 squared minus kq squared over r1 squared over also in the j direction. Okay, and to simplify this a little bit more, we can see that we have fq. The first term we got to keep it the same. There's no real simplification. We can put here kq squared over r3 squared in the I direction. Don't forget these are important. Plus 0.2 k q squared over whoops, my bad, those don't work out. Can't factor this out anymore. In fact, that was as simple as we can get it just above there, so let's actually just sub in the numbers now. My bad. Okay, so multiplied by k, which is 9 times 10 to the 9 times q squared. And we know that q was given to us as 3 microcoulombs times 10 to the negative 6 squared. And this was associated with R3, and we know that R3 was 0.05 meters. Square that, and that's in the I direction. And in the j direction, we're going to have 1.2. Let's actually factor out the kq squared from both of them. So like this. 9 times 10 to the 9 times 3 times 10 to the negative 6 squared multiplied by 1.2 over r3 squared, so that's 0.05 squared minus 1 over r1 was 0.03. Yeah. Squared in the j direction. Okay, let's send this to the calculator to figure out what that calculation is going to be. So we got 1.6 times 9 times 10 to the power of 9 times 3. Oops. Times in brackets 3 times 10 to the power of negative 6 squared. Divide by 0.05 squared. Okay, so our FQ value. Here we're going to have negative 51.84 in the I direction, plus, okay, so here we're going to have something different. We're going to have 9 times 10 to the power of 9 times, in brackets, 3 times 10 to the power of negative 6, close bracket, squared, times, in brackets, 1.2 times 0.05 to the power of negative 2 minus 0.03 to the power of negative 2 and And my result for this is going to be actually a negative number. So just erase that so there's no confusion. Minus 51.12 in the j direction. Okay, so our magnitude of this is going to be under the root just looking here to see what the written input was. What was the magnitude of their force calculation? Because I don't think that it wouldn't be possible for you to get like a net force of 23 degrees, because that's going to be lower than both of the components combined. That's peculiar. Okay, let's just proceed as usual. So we'll have under the root here, we'll have 51.84 squared plus negative 51.12 squared all under the root 51.84 squared plus 51.12 squared. So here I got 72.8 Newton, and the angle at which this is going to operate is going to be like this. So because they're both negative like this, we know that the angle is going to be must have this direction towards like the southwest. Okay, so to do this, we will do angle is equal to the tan inverse of the FQY component divided by the FQX component, which is going to be tan inverse of negative 51.12 over negative 51.84, and our angle is going to be like this. So it will be inverse tan 51.12 divide 51.84. We don't really need to worry about the negatives because they're going to cancel each other out. And this will correspond to 44.6 degrees. And since we know that the direction is like this, we know that the real angle add 180 degrees. So the real angle, this is relative, so our real is 180 degrees plus 44.6 degrees, which is equal to 224.6 degrees, or approximately equal to 225 degrees. Okay, and that's what they said is going to be the case here, but that force is definitely wonky. Okay, so I'm a little bit concerned about the force that they give in here, but yeah, so this was a solution that I got. The angle is going to be 225 degrees about, which is the same as what the person said the book was going to be, and the force magnitude is going to be about 73 newtons is what I calculated, which is unknown here. But yeah, this would be how you calculate it. So you just want to find the components, add up the components, and then once you have the components, getting the angle and getting the magnitude is fairly straightforward from there. You just need to know that you want to set up your components. First, you want to set up your total angle. You want to get your magnitude, and then attach a unit vector direction vector, which is what we did with like the I and J stuff. Especially here, that's like the main meat and potatoes of this. So once you get that good, everything else should fall into place. So for here, of solution does not have a clear answer for the etude. Does not have a clear numerical answer for the magnitude. And the angle is wrong.